Ramanujan for G is now available on the Google Play Store. Try it out for free.
So, hi students. So today I was just going to provide a full roundup of the whole heat section, you know, and we will try and mix and match all the parts of it. Heat is, there are multiple sides of this whole heat understanding. There is the work side of it. There is the thermal properties of matter side of it. Then there's the thermodynamic side of it. So these are three different legs, completely related, and they take a step from here into chemistry as well. The physicists, they look at this a little different. The chemists look at it a little more different. And in chemistry, they also introduce the whole thing with this equilibrium. The whole equilibrium equation with Le Chatelier's principle, etc., which comes into play. And on top of that, there is, of course, the kinetic theory of gases taught somewhat differently, but I will provide you the physics side of this whole relationship, of various things, the multiple states of matter. Provide a very quick roundup of all the parts so you understand how the various things are related. So this is going to be a little bit different. So let me get going. In terms of how we go about providing this. So at the most basic level, when we look at matter, matter consists of solids, liquids, and gases. And solids, things stay in one place. The atoms stay in one place. If there is some kind of conduction or this of heat, right? Then the electrons, there is a energy transferred as heat from one place to another. So if there's electric, there is not electric. I mean, if there is thermal conduction, right? There is heat transfer from one place to the other place through something. If something is hot, it spreads evenly out through the metal. If something is a metal, right? Not so with other substances. Now, solids have a different way of interacting versus say gases. Gases on the other hand, solids have definite shape and definite size and that is because they are the atoms, at least the nucleus of the atoms stays very fixed. So when you apply pressure, you are able to only move some of the atoms from here. So if I move it, the location of the atoms vis-a-vis each other stays in a fixed phase. That is, the nuclei stay in a fixed place. Now, if anything that can be moved in a solid, only the electrons can move. So when you apply pressure, the change in the volume is negligible and maybe so small that it cannot be recorded. Okay? Now, for liquids, the same is true, but since it cannot take like shear stress, it does not have definite shape and size. So it takes the shape of the container that it's put into. So in the case of liquids, they are not they can move vis-a-vis each other. So like when you tilt a vessel, the atoms actually move. Because they are not so tightly coupled with each other, so they can kind of move, and therefore it can never take any shear stress. You put your hand through water, you're actually moving all the nuclei from one side to another. Okay, so they are little bit loosely coupled. In the case of the gas, by themselves they are moving all around. Okay, so that's the three different fluids. When we fill an automobile with tire, the air does not go to the bottom. Okay, it fills the space. Like for instance, right now there is an atom here. And in many ways it's defying gravity because they have much more kinetic energy to bounce about and move around, and they never go and settle down in the ground at any time. Because they have too much kinetic energy. In the individualized atoms, the individualized nuclei, they just flow all the way. Okay. Now, so liquids and gases, they do not take specific shape. Therefore, they are what are called fluids. So that's what we are discussing here. We say liquids and gases are fluid because they can take the shape of whatever container. There is this thing in Advaita where they talk about the vessel, right? Water takes the shape of the vessel, right? The vessel itself takes is shaped not by the clay that it is made of, but by, so it's a deep idea that they are trying to convey. So what is the idea there? So that's a different that's a philosophy. We are talking physics here. So now there is and so when we talk of the physics, right, and we are talking about fluids, there are two kinds. One is the liquid, which goes to the bottom. There is gravity, which plays a role in the liquid, and but then they can move vis-a-vis each other. The solid, when you move something vis-a-vis each other, they generally don't move unless you are hammering it, and then they compress a little bit, they move a little bit this way, that way, they deform. Okay, so now this is all about fluids, therefore, so they can move. No, but there is another state of matter which is called plasma: solids, liquids, gases, and finally plasma. Okay, now in plasma, this happens at a very high temperature in the sun. Okay, so now all the atoms have lost all their electrons. Okay, from the outermost, they're actually stripped of the electrons from their outermost shell. They all are ionized, and then all these ions are kind of pressured together, and this state of matter is at a very high temperature. This state of matter is called plasma. It's kind of like, like in the sun, the sun in the sky, right? So it's kind of moving together. Now, the air we breathe is fluid. People think that colloids are in some ways different, because they are suspended particles in something like milk that can be considered separate state of matter. But I don't know about that. So mainly there are three states of matter: solids, liquids, and gases. And then there's the fourth state, which is plasma, which is in the sky. Okay. Now, the human body mostly consists of water. We are 90% water, and a lot of processes that come in the human body, including plants, are mediated by fluids such as water. Okay. So now, the interatomic perspective is what I've been explaining to you. Intermolecular forces of attraction in liquids is small but not negligible. So it's intermediary between the solids, where the intermolecular forces are very strong and very large, and that keeps the molecules stay together in a fixed shape. While in the liquid it's smaller, so they can kind of form the vessel, whatever vessel a solid vessel can offer them. Okay. Now, they do have issues with respect to gravity. That is, they will always sink to the bottom. But not so with gases. Gases occupy a space, and all of it. Okay, so that's how it works. Okay, so and therefore there are differences in all this. Okay, so now a block of wood or iron which is heavier, that we know, right? That is decided by the density, rho, right? So it is the mass per unit volume which is different. So that is a intrinsic property, right, of each element, right? So a coal has a different density, right? That is because each atom is different, and on top of that, you also have the aggregate value, right? When we talk of the aggregate value, we talk about density. When we talk of the atomic side, we talk about the atomic number, which is largely decided by the number of protons plus neutrons. We teach that as part of both physics in class 12, and also as part of the chemistry, right? So rho equals mass per unit volume. We call the density. Density is typically not an intrinsic property in the case of gases, right? In the case of gases, we talk of, at this pressure, what is the volume? Okay, PV, right? And that is decided largely by the ideal gas equation. PV equals nRT, right? Now, on the other hand, solids, liquids do have a density, and solids do too. Therefore, that's how we discuss this anomalous expansion of water, right? Water ice is at water has or itself has three states, right? Ice, water, and water vapor, right? And of the three, 4 degrees, the liquid water has the highest density, right? And ice itself is less dense than water, and that is called the anomalous expansion of water. Okay, so now then we came up with the units, and then pressure and temperature will affect the value of density, right? So typically pressure and temperature, when you increase the temperature, things expand, right? As you increase the temperature, it will expand. That is true of all types of matter, right? The interatomic forces weaken when there is the agitation due to temperature. Temperature can be thought of in that form, right? Gases have density 3 orders of magnitude less, right? They expand. The expansion, akasha, the elements, the expansion is there with gases when compared to solids and liquid. There is the force of attraction is negligible, right? So typically the questions in this area deal with things like density, etc. So what is the mass of a lead sphere of radius? You can easily find mass per unit volume. Rho is the mass per unit volume, and therefore if you had radius, so 4 by 3 pi r cubed, then rho times 4 by 3 per volume, right? So volume, you use whatever formulas you've got, right? So that is a simple set of ideas, very simple. Now the next set of ideas we did discuss was dealt with the thermal properties of matter. So this set of ideas, um, here we we dealt with thermal. When we talk of thermal properties, we talk about heat, and then we talk about temperature, right? And so now there are two things that happen when temperature is added to when heat is added to a body, right? It's uh, on the one side, the natural tendency is when you add heat to a body, its temperature rises, right? Until it reaches a certain level, in which case there is a phase transition. We have solid, liquids, and gases, so it transitions to another state, right? So at lowest temperatures, a body will remain a solid. As you keep heating it, it will go through a transition from solid to liquid at a fixed temperature, and that at that temperature there is a phase transition from solid to liquid, and we don't define the specific heat during. So as it heats up, we talk about the specific heat capacity, and then we talk about the latent heat capacity at the transition point when it absorbs a lot of heat. Let's say you have a mass of m, right? Then it absorbs all that heat, and then you have a latent heat capacity at that particular temperature when it completely converts from solid to liquid. Okay, so because liquid is a very different form, so then you go from solid to liquid, and then so you then have this latent heat which comes into play. So now the specific heat, when you just heat it up, ms delta theta, delta q equals ms delta theta. Heat in the form of energy delta q comes into the system, gets transformed, ms delta theta. Okay, now remember that typically when we do thermodynamics kind of situations, we do heat loss is equal to heat gain. But remember that in the true form, it is not just heat is heat, right? Heat gets transformed into work, and that process of transforming heat to work is what thermodynamics is all about. That is the dynamic side is the work, and that is how the steam engine works, right? So, and these things have been quite well understood, for now. Now, the centigrade, there are the three scales of temperature. Temperature comes in three scales, and we already discussed that. There is the Fahrenheit scale, which is used in the United States, or Fahrenheit is a German word, right? Now, then there is the centigrade scale, which is used in many parts like India, right? We speak of centigrade, it's a British system. Finally, there is the Kelvin scale, named after Lord Kelvin, who's a Britisher, right? And the Kelvin scale is the absolute scale. So in the Kelvin scale, there is an absolute zero below which the body cannot go below that 0 degrees Kelvin, right? Um, Now that is, in fact, there is no body that typically goes to zero. It represents a state in which everything is at complete rest. Okay, and that 0 degrees Kelvin is negative 273 degrees Fahrenheit. The Each increase in 1 degree Kelvin is equal to 1 degree centigrade. Only thing is the scales are, there are two scales, but the zero here, 0 degrees centigrade, is 273 degrees Kelvin. So there's that much lower you can go. Negative 273 degrees centigrade is absolute zero, but you cannot go below absolute zero. Okay, so the Kelvin scale starts from zero, and so normal temperature is about of 27 degrees in, say, India, which is thought of as good weather, is 300 degrees Kelvin. 27 degrees centigrade is about 300 degrees Kelvin. So 273 degrees Kelvin is 0 degrees centigrade. 0 degrees centigrade is the point at which water typically freezes. Okay, under normal standard temperature and pressure, water changes form from solid to liquid at 0 degrees. Okay, so now, ideal gas equation, we have Boyle's law and Charles' law. Boyle's law is PV equals a constant, and Charles' law is V by T equals constant. And therefore, when you combine Boyle's law and Charles' law, we have PV equals nRT, which is called the ideal gas equation. R is 8.31, and is universal gas constant, right? And therefore, N is the number of moles. And each mole consists of an Avogadro number of particles, which is 6.023 into the power of 23, right? Particles, right? So PV equals nRT. Pressure is a force per unit volume, newtons per meter square. Volume is V cubed, and therefore you find the corresponding P times V is the same unit as work. Therefore, that is joules. Therefore, joules per R is joules per mole per Kelvin. Because of that, okay, P times V is joules, work, the unit of work. Okay, unit of heat also. Joules is also the unit of heat. We measure heat in the same units as work. Okay, so because these are all variations of energy. Okay? Now, when most objects expand when heated, metallic liquids can be opened by placing glass, and if it's like in a tight container, they do that, tuck tuck tuck. Then you can open a bottle, hermetically sealed bottle, right? Now, balloons shrink when placed in ice water. Why is that? Why do balloons shrink when placed in ice water? Because when you cool it down, PV equals nRT, right? When you cool it down, you're decreasing that is because of Charles' law. You cool it down, the temperature goes down, the volume goes down, pressure is kept fixed, right? And therefore it softens, right? So now the length, right, of something increases in linear expansion. So when you heat something, there is thermal expansion, right? So area and volume increase, respectively, using this, right? PV equals nRT, right? So now we then define thermal coefficient of expansion, right? And we said that the thermal coefficient of linear expansion versus the thermal coefficient of volume expansion. Volume expansion will be approximately 3 times linear expansion, though not perfectly, right? But typically you can use that delta L by L equals alpha times delta T, linear expansion, right? You increase the temperature by 1 degree, the object will go up, alpha times 1 degree, right? So it's a linear scale, but really it's not linear. It's kind of linear over short periods. Okay? Everything is incrementally linear. Then we discuss the anomalous expansion of water. Water is the most dense at 4 degrees when it's a liquid, and ice, which is a solid, is actually less, floats in water, right? When you drink, say, Coca-Cola, you ask, today very cold, so I put a piece of ice, so then it floats in the water because the water expands anomalously. Okay, that is called the anomalous expansion of water. Below 4 degrees to expand again. From 100 degrees, it starts to become denser and denser and denser, but after 0, it again expands. And when it becomes ice at 0 degrees, typically, right? So this is very anomalous, right? Normally, you have solids the most dense, liquids less dense, gases even less dense, right? So that is why it's called anomalous. Okay. So now PV equals nRT. Then therefore we define this coefficient of volume expansion. P times delta V equals mu times R delta T. PdV is work, right? If you don't have dV, then you don't have work, right? VdP is not work. Okay. So coefficient of volume expansion and coefficient of linear expansion and thermal stress, right? So therefore, alpha V was 3 times alpha L, right? So they are related with each other. Delta V equals I plus delta I whole cubed. So then you have, if you have delta V, it's I plus delta I whole cubed minus I cubed. So that will equal 3L squared delta L. The second term, which is 3 L delta L square, is dropped in the calculation. So you have delta V by V equals 3 times delta L by L. That's how you end up with. This equation means that alpha V equals 3 times alpha L. Delta V by V is alpha V. Delta L by L is alpha L. Okay, so thermal stress is the stress that develops in a rigid truss that is held in place and expands as a result of its expansion or inability to do so. So now the delta F by A equals stress by strain is a constant, right? So that is Young's modulus. What is the constant? Young's modulus. So stress is what? Delta F by A. Strain is what? Delta L by L. The increase in length by the original length, right? Strain has no units, right? Stress has the same units as pressure. Okay. So when you apply pressure, you end up with this equation. Now, then we discuss the specific heat capacity. S is equal to delta Q by delta T, right? M as d theta, right? Heat capacity is S, right? Then we introduce specific heat capacity, which is M as delta theta equals delta Q. And then we introduced, say, various problems where you do heat loss equals heat gain, right? So molecular specific heat capacity pressure. So then we introduce this contraption called calorimetry, which is to understand this specific heat capacity. We isolate the body from heat coming in and typically work also, and therefore we talk about adiabatic, etc. Right? So now gold spheres placed, and therefore we then use heat loss is equal to heat gain. Heat loss is always ms delta theta, etc. Right? So heat gain is also ms delta theta. So one loses heat, the other gains heat. Right? Then we introduce the change of state where there is latent heat comes into play. Right? So and then we have vaporization, which is change of state. So and therefore we have these phase diagrams. Triple point, the point where all three elements coexist at a given temperature. So there's a red line is the sublimation curve, green line is the fusion curve, blue line is the vaporization curve. Therefore, we say Q equals ml. Ml is the latent heat of vaporization. Latent heat of fusion is Lx. And therefore, that's how we end up with these things. So amount of heat lost by water, ms delta theta. And amount of air, so that we most often use that equation. Heat loss is equal to heat gain. So that is what you use in solving all these simple problems. You typically get some questions with that. Now, heat conduction happens when I'm sure you have kept a different types of vessels in the stove, right? Or in a cooker, right? Cooking range, right? The metallic vessels are used in cooking, right? Why is that? Because metal will conduct. Okay? And it conducts is a very good conductor, just as it is also all electric conductors are just as good heat conductors, right? In electric conduction, typically they use copper, right? Copper is very much used in electric conduction. All the wires inside they will have copper. Maybe there is a few one which will have aluminum, right? But copper is the most common conductor. It is a very good conductor of electricity and also good conductor of heat. Now, when we look at heat conductivity, the heat transfer is Ka dt by dl. Okay, the heat conductivity, how quickly is, there is a thermal conductivity constant, Ka delta theta by L, right? So that is the heat conductivity of a substance. So remember that formula. So here is a problem. Uh, an iron chain and a gold pendant melded together. The iron chain is at 400 Kelvin. Gold pendant is, so what is the temperature at the junction, right? So at the junction, H1 will equal H2. Okay, and H1 is Ka delta T by delta L, and K2A2 delta T by delta L, right? So the common junction is on this side it is a Ti, on that side it's a TL, but at the junction it will be Tc. So then they will readjust to achieve that H1 is equal to H2. Okay, so so then using that you can then solve for Tc. Okay, so at the junction they will then adjust to a certain pressure. So that is how thermal conductivity occurs. Okay, so now then we discuss convection. So conduction is when the heat flows without the molecules flowing. Convection happens through the actual movement of the atoms or molecules. Okay, water vapor also rises and creates, there are all these currents. Currents is when actual atoms move. Okay, in the water also there are air, there is water current, right? The things move, as you have seen. If you see a flood, you can see how quickly water moves, right? And air moves even faster, right? And in air, the movement of the air is what are called various trade winds. They create what are called currents, different currents. There are water currents like the North Atlantic drift, and then there are air currents which also produce air, and so that interaction produces a lot of oceanography and heat and water interaction. Okay, now then when infrared light rather than electromagnetic transfer, because this is no medium, it is radiation. All bodies with temperature radiate energy. Red hot iron or a lamp exhibits thermal radiation. So then we have Wien's displacement law, lambda m times T equals constant. And finally, we have Stephen Boltzmann's law, which says that for a radiational body, right, the heat that a body radiates is proportional to the surface area times the sigma, which is specific to the body, times the fourth power of the temperature. Okay, so that is what is called Stephen Boltzmann's law for black body radiation. A sigma T to the power of 4. A is the area, surface area. Sigma is the specific heat for the particular body, and then the temperature is the absolute Kelvin temperature to the power of 4. Okay? So Earth absorbs energy from the sun, and but then there are certain gases like the greenhouse gases in the atmosphere which also absorb energy. Okay? So typically the Earth acts like this. It absorbs the sun's energy and then it reflects it off. If there was no atmosphere, it will just absorb it and then it will reflect it. So it will stay in a temperature equilibrium. But then there is, an atmosphere. The atmosphere, certain gases, they just keep absorbing the energy and they start moving faster and faster. And as a result, they absorb that energy, and therefore there is a rise in that temperature, and eventually that leads to other changes in the land and in the water. Therefore, when more of that gaseous energy is passed on, is held by these GHG gases, and then transmitted to the water as well, then there is more melting, and therefore of the ice caps, and therefore that is the theory behind greenhouse effect. So so that is finally we look at Newton's law of cooling, which says the rate of loss of heat is proportional to the difference in temperature. So dq by dt equals minus k dt, and so when you write dq as m as dt, then you have a ln, when you integrate dt by t minus ts, you end up with a ln equation. Therefore, you have a exponential equation, right? So see, if you have an equation like this, right, ms ln t minus t naught equals k t, where t is temperature, t is time, right? Dt is rate, anything with rate, right? Rate means it's the time it takes, right? The rate of loss of heat is directly proportional to the difference in the temperature from the surrounding. Surrounding temperature is a constant, and this temperature, the body's temperature, will decay down to the surroundings temperature. Okay, and when it's much hotter, it will decay faster. When it is less hot, it will decay slower. Therefore, you have a differential equation, which when you solve using what is called variable separable, so you have dq equals ms delta dt, ms dt divided by t equals minus k times t minus ts. You take the dt to the side, bring the t minus ts down, then you do the integrating ms ln t minus ts equals kt plus c. Before you end up with this T equals T environment times e to the power of minus RT. Therefore, then you can solve problems using this. There are two ways to solve these problems. One is by approximating this differential equation, right? And the other is, of course, to use the T equals T environment plus this equation. Okay, so this equation this is an approximate way of looking at it. You take the intermediate temperature and then you use that intermediate temperature as a average, and how how long it will take, right? So this is all about how long it will take. When you here's how it happens. When the temperature is very different between the surroundings and say a hot body, it will cool fast. But when it comes very close to the surrounding temperature, it will cool even slower. So that was the next idea that we brought up. The final idea that we are going to look at is also it deals with thermodynamics. Right? Thermodynamics, of course, is taught over many classes, as many of you know, right? And so, but then today we are doing only a revision, right? So, so because of that, what I'm going to do is I'm going to do a whirlwind tour of thermodynamics for you, rather than, and why we do that is so you are able to use such a, the basics level understanding to quickly solve some ease, you have a full, well-rounded conceptual understanding, so that you can have quick recall and you can quickly zone in on what kind of problem it is, whether it is thermal properties of fluids, conduction, convection, radiation, right? Mechanical properties of fluid, thermal properties of matter, or thermodynamics. Various parts of these three, they kind of coexist and co-interact with each other. So that's why we are doing this in this whirlwind form. Okay, so in thermodynamics, we first introduced, then we introduced kinetic theory of gases, if you remember, right? So I'm not going over kinetic theory of gases here. In kinetic theory of gases, we then explain how gases work, how you reach PV equals nRT, right? In the ideal case, and then also there is a real gas equation, which is a little bit different. T minus A over V square times V minus B is a constant, rather than PV is a constant, which is Boyle's law, right? And so now we then introduce this machine called a heat engine, right? So first we introduced this idea of a system, right? The idea of a system was then we said that there is a conservation of heat and energy together. Heat gets transferred to work, right? Then we said that there is this other law called the second law of thermodynamics. The first law of thermodynamics deals with basically conservation of energy. Third law of thermodynamics states that the temperature cannot go below absolute zero. Okay, the second law of thermodynamics introduces this concept called entropy. And so in order to understand this, we introduced this idea of a Cardinal engine. Then we looked at T versus V on the one side and T versus S on the other side, S being entropy, right? So Q is equal to TS. So entropy has the units of joules per Kelvin, right? Then we introduced the Carnot engine, where there is there are two types of expansion, isothermal and adiabatic. And then we explained two types of engines. One is the heat engine, the other is a heat pump. And in one case you do work, and in the other case you you kind of increase the you make a colder body colder by doing work on it. Okay, and in one case you use external effort to make a colder body colder, right? So this is how these things work. Okay, so with so in that context we introduce the Carnot engine, right? We introduced the Carnot engine and the refrigerator, right? So the heat engine, right? So the heat engine, it works in a complete cycle. Basically, there is a hot body which there is heat transferred from a external body to a system, and that the system then does work. Heat engine. The most common case of the heat engine is the IC engine. There is a slight difference in the case of the IC engine. It is not exactly a system, rather it's a control volume, in the sense that the fuel that you burn is a gas, like say a car is a gasoline fuel, which then gets converted to carbon dioxide, and the carbon dioxide goes out of the exhaust, right? So it is continuously goes out of the exhaust, right? So now what then happens is there's a body at a very high temperature T1, which then transmits a certain amount of heat to this body, and then that does work and goes out. And then some of that the uh, second law of thermodynamics, as stated by Clausius or Kelvin, right? One of the versions states that when you convert heat, you cannot convert it completely to work. You will always have this Q2 also going into the ambient temperature, right? So Q, and therefore we define the efficiency as the work done, W, divided by the Q1. And there we discussed, the thermal plant. The thermal plant is where typically in India, particularly, we burn thermal coal in a thermal plant. In the United States, they also use another fossil fuel called natural gas, which is burned, and then they produce electricity, right? So electricity is produced by the work, right? And so the efficiency is measured as the amount of work done to the amount of heat transferred. Now, typically, the amount of Q1 minus Q2, right? So here Q1 is what is pushed in, Q2 is what goes out as heat, and W is what is the work, which is the benefit that we get in terms of the work done. So Q1 minus Q2 equals W is from conservation of energy. Heat is a form of energy, right? So Q1 equals Q2 plus W. W over Q1 is the efficiency, right? So can you have an efficiency of 1? No. The second law forbids that efficiency, right? So therefore, so that is how that works, right? Now then you have a second body which is called a heat pump. In a heat pump, a refrigerator is a heat pump. It takes heat away from a colder body. So how do you take heat away from a colder body and give it to a warmer body? Because that normally doesn't happen, right? We just looked at Newton's law of cooling, right? Newton's law of cooling happens when heat goes from a hot body to a colder body for typically the surrounding temperature, right? Then the surrounding temperature stays constant, right? It just gets, because it's the ambience is infinite, right? Now, but then in a refrigerator, we take heat from a cooler body and transfer it to a warmer body. We do the reverse. How do we do that? We do that by doing work, right? And the work happens in the form of compressing that freon, which sits inside the fridge, and then we make it liquid. Then it gets done. As it heats up, right? It then becomes gas, and then it's again compressed and made into a fluid, into a liquid, right? So when you compress it, freon has this property that when you compress it, when you apply pressure, it becomes liquid, and then that when it flows through it again becomes gas, and then it has to be compressed again. So it goes in a cycle, right? So it's a system on which work is done, and so that is a refrigerator. So now here the system, work is done, and therefore it transfers energy it takes energy from a cooler body and transfers it to a hotter body. T1 is always greater than T2 in both the engines, right? So, but then here there is work done on the system, and therefore we again there is you cannot have this thing called COP, right? COP is Q2 by Q1 minus Q2, right? So Q1 here, right? So the work done, right? Some of it goes as Q1, right? And some of it comes in as is transferred as Q2. Q2 is what you want, right? W is the effort that you expend, right? W is the effort that you expend. Q2 is what you want. This is the fridge. This is the vegetables, right? So the vegetables are being cooled, right? So you take heat from the vegetables and then you pass it to the outside atmosphere. And some of that comes also from the work directly gets transferred into the outside. So you ideally want a lot of Q2 going to the outside, right? You want all the work coming from here. You don't want a portion of the work transferred being greater, right? You want all the Q2 going outside. That can never happen. In which case, you don't have to do any work, right? So if Q1 minus Q2 equals 0, that can never happen. That's another way of stating the second law of thermodynamics. And so then we introduce this idea of the Carnot engine, right? So this is a perpetual motion machine. Perpetual motion machine of the second kind is not also forbidden. Okay, so the second law forbids the the case where you completely transfer heat from a cold body to a hot body. So that is the Clausius statement. Okay, so if there is the sole result to transfer heat from a colder object to a hotter object is not possible in a cyclic process. That is the Clausius statement, but actually it is the same law. Okay? Now Kelvin's statement is the case of the heat engine. Clausius statement is the case of the heat pump. So, but in both cases, we are actually stating the same law, and it is the second law of thermodynamics stated in two forms: Kelvin statement or the Clausius statement. Okay, so that we discussed. Then we introduced this idea of a reversible engine, which is a Carnot engine, and then we looked at the area under the P versus V curve versus the T versus S curve, and then we said that if you, let's say you take a heat engine, the work done by the heat engine is in the P versus V curve, the area in the PdV curve, right? PdV, integral PdV is the work, so the area under the P versus V curve, if you had a cyclical process, the area inside that quasi rectangle is the work done. So the ratio of that to the heat, the area in the T versus S curve, TdS is the heat, right? So TdS, area in the T versus S curve, that will give you the heat, and TdV will give you the work. So work by heat gives you the efficiency, right? And the efficiency is always much less than unity. But then what Carnot goes on to say is that the Carnot engine is the most efficient that you can ever be, given how entropy works. Okay? And entropy works against you, right? So you have two isothermal and two adiabatic processes in a Carnot engine: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, right? So that's the Carnot engine, right? So in the Carnot cycle, he went on to demonstrate how these two things work. P versus V curve, the T versus S curve. P versus V curve. Area under this will give you the work. The area under this will give you the heat. Therefore, the ratio of this to that is your efficiency. Okay, and so you have two equations. The isothermal case, PV equals nRT. If T is constant, isothermal, right? Then you have the corresponding equation, nRT ln V2 minus V1, V2 by V1, right? So then in the adiabatic case, PV to the power of gamma equals constant. Then you have a corresponding equation, right? And that equation is given by the first case work was RT ln V2 by V1. The second case R times T1 minus T2 by gamma minus 1. When you do the integration for the work in the second case, right? And then you subtract the other two, right? Therefore, when you subtract the other two, you therefore end up with the total work, right? And when you take the equation of the W by Q1, you end up with this 1 minus T2 minus T1. The efficiency, therefore, 1 minus T2 by T1 for a Carnot engine. So, and therefore, it operates in TH and TC. So, 1 minus TH over TC T2 by T1 give you the efficiency of the Carnot engine. So, and therefore, we explained these details. So, I did a whirlwind tour of the Carnot engine so that you kind of get a full idea. And finally, Carnot's theorem, he says the efficiency of all reversible engines working between two reservoirs, is the same. If you have two temperatures T2 and T1, you have two reservoirs. The best you can do is the Carnot engine. The Carnot engine has the maximum efficiency, and it is not one. It is 1 minus T2 by T1. Okay. So that is the very specific idea that you must learn from Carnot's theorem, and you can of course prove that by considering a something better than the Carnot engine, and you will find that it violates the second law of thermodynamics. So I did a whirlwind tour of everything in with respect to heat for physics. Of course, this has nothing to do with the chemistry side. You must do a lot more in chemistry, and because it's a very central idea, in chemistry as well. Thermodynamics is very important in chemistry as well, and of course in physics as well. So with that, I'm going to conclude today's class and this was done with the aim of giving you a very, an understanding so that all the parts fit in, So you do this whole quick rapid run through tells you there are all these different things that are happening, because they can ask you mixed questions where you do heat loss equals heat gain, and at the same time you do little bit Carnot engine, same time you do some conduction. So you must know in which part the question is expecting you to apply, which particular set of ideas they're asking you to apply. So that is a very critical factor that you have to learn to use in thermodynamics. Okay? So with that, I'm going to stop for today, and I'll see you all again next time.